Hello and welcome. For this set of notes, we are still going to focus on the stability of an atom's nucleus. So we are first going to talk about what a half-life is, and it's going to help us describe the rate of nuclear decay. If you looked up the definition of what a half-life actually is, you're going to get this definition. So it's the time required for half of a sample to decay. So looking down here at this example, you can see at time 0, you can see it's shaded very dark, and then after one half-life, half of those original particles have decayed, and then after two half-lives, the remaining half has decayed again, and then the remaining half decays again and again and again and again, and as you can see, as time progresses, less and less of that original particle or atom exists, and it turns into a new isotope. And so in past notes, we have talked about the stability of an atom's nucleus, about the 1-to-1 proton to neutron ratio, and knowing that elements that have an atomic number 84 or higher are more likely to be unstable because there's more protons and neutrons in the nucleus. If we know an atom's half-life, the longer the half-life is for an atom, the more stable that nucleus is. So if we are comparing two samples and one has a half-life of 1,000 years and one has a half-life of 5 days, longer half-life, 1,000 years, is more stable than the 5-day. Here is another example showing a graph of some atom going through a half-life. So starting here at time 0, we are given two kind of examples. So the original atom we call the parent atom, and what it will turn into once it goes through a half-life is called the daughter atom. You can see it by the colors above. So at time 0, we have 100 atoms starting with for the parent atom. After it goes through one half-life, those original 20 atoms will decay, and so we have 10 remaining of the parent, and now 10 newly formed daughter atoms. After the second half-life goes on, those original 10 of the parent atom will decay into half again, and then so we only have 5 remaining of the parent and 15 now of the newly formed daughter atom. Another half-life goes on, so that 5 will decay into half again, 2.5, and it turns into the newly daughter-formed atom. So as you can see, as time progresses on, after each half-life, half of the original will decay and form that new daughter atom. For this example, we are going to start with 100 grams of the isotope carbon-14, and we know that half-life is 5,730 years. So 5,730 years goes by, and half of this sample, half of this 100 grams is going to decay. So only 50 grams of the original sample remains. And then another 5,730 years goes by. Now we're up to 11,460 years. So only 25 grams of the original sample remains because it's half of that from the 50 decays. And then another 5,730 years passes, and now we're up to 17,190 years, and only 12.5 grams of the original sample remains. Everything else has decayed into a new daughter atom. Now this example is asking something a little more specific. So it says the half-life of phosphorus-30 is 2.5 minutes, so very short half-life. Short half-life means unstable nucleus. If you start with 35 grams of phosphorus-30, how many grams would remain after 20 minutes? So we could do basic math and calculate this every 2.5 minutes. So for the first half-life, again, we are starting with 35 grams of phosphorus-30. So the first half-life passes, 17.5 grams remain, and that was after 2.5 minutes. The second half-life goes on. So half of 17.5, we're now at 8.75. Now we're up to 5 minutes. The third half-life, half of 8.75, now we're at 4.38, and 7.5 minutes have now passed. Now we're at the fourth half-life, and half of 4.38, we're down to 2.19 grams of that original sample remains, and now we're at 10 minutes. Okay, we still need to get to 20 minutes, so the fifth half-life, 1.09, 12.5 minutes, sixth half-life, 0.55. So I'm just taking this previous number and dividing it by half to get the next amount of grams that remain. And we are up to 15 minutes. Seventh half-life, half of 0.55. Now we are at 0.27 grams remain of that original sample. Everything else is decayed into a new daughter atom. Now we're at 17.5 minutes. And the eighth half-life, we have 0.14 grams remain. And now we're at our 20-minute mark. So we can do this and just keep adding up the time and dividing the original sample in half, but I could have asked this question to get to 40 minutes. So doing this all the way up to 40 minutes can get kind of time consuming. So I'm thinking, is there a faster way for me to do this type of calculation without having to add up the time and dividing the sample after each half-life? And the answer is yes. There is an equation for us to use to quickly solve for how much of the isotope remains, or how much of the original amount of the isotope we started with, or maybe we're asked to calculate the number of half-lives. So for our equation, I'm going to rewrite this just because it didn't transfer over when I copied this. So it's A equals A sub naught times 1/2. I like to tell students just to plug in 0.5 into their calculator, raised to the nth power. I'm going to change this down below. So looking here, what do these variables stand for? And please do not memorize this equation. This equation will be given to you if you printed out that chemistry reference sheet that is in our course resources folder. This equation is also on the back of that. So A stands for the amount of isotope remaining. A sub naught stands for the original amount of isotope. N stands for the number of half-lives. So it's not always going to give you the exact number of half-lives in the problem. You might have to calculate it. So it might give you the total time and the half-lives, and you just divide those two. Other problems might give you the number of half-lives and the total time, and you have to solve for the half-lives. So we will be presenting you with a variety of different questions, and you should be able to determine any of these variables presented to you in this equation. So let's go through an example using that equation. So let me write the equation up here again. A equals A sub naught times 0.5 or 1/2 raised to the nth power. So we have an example of palladium 100. The isotope palladium 100 has a half-life of 3.6 days. If you have 6.02 times 10 to the, this should be 23rd, raised as I put up as a subscript, or superscript, I'm sorry, atoms at the start, how many atoms would be present after 20 days? So let's go through and identify our different variables, and then we can plug it into the equation and solve for our answer. So we are asked to solve for how many atoms would be present after 20 days. So we are solving for A. They are telling me that the original amount of the sample is 6.02 times 10 to the 23rd atoms. You have, so that's how much we are starting with. And then it is telling me that the half has a half-life of 3.6 days, and it's telling us that 20 days have passed. So that's our total time. So we first need to solve for n, which is total time, divided by the half-life, which is 3.6. And I get 5.56. All right, so now I have my variables. I can plug it into my equation. So again, I'm solving for how much remains. So A equals 6.02 times 10 to the 23rd times 0.5 raised to 5.56. So I type this into the calculator. Again, make sure when you are typing a number into scientific notation, it's best to use that exponent, the EXP button or the EE button, just so we avoid any calculation errors. And you should get 1.3 times 10 to the 22nd atoms. So the last little bit of notes here, we are going to talk about nuclear energy. So we have something called nuclear binding energy, and this is the energy required to split a nucleus of an atom into its components, meaning the protons and the neutrons. So you can see here in this picture, we have a nucleus plus the binding energy, and it's going to break apart into its individual components. The positives are my protons, and the ones that do not have a charge are neutrons, because neutrons do not have a charge. So back at, I think that it was our second part of our notes, we talked about the strong force, and that was this force that keeps the nucleus from breaking apart. So the greater the binding energy, that means the stronger, the more stable the nucleus. So also, if you see over here, there is a greater mass, and over here there's a smaller mass. So that means, if you kind of look at this reaction in the reverse direction, that as these protons and neutrons come together, some energy is given off and we get a nucleus that has less mass than the individual particles. So what happened to that mass? And what happened to that mass is a little bit of it was destroyed. So back when we talked about chemical and physical reactions, we also talked about the law of conservation of matter, saying matter is neither created nor destroyed. Here we are going against what we just said, and that's kind of where we have a difference between chemical and nuclear reactions. So because matter is destroyed, the mass of the nucleus will be less than the total mass of its original particles. And that is called mass defect. So some of you might be familiar with this equation, E equals mc squared. This E stands for that energy, and this is the mass, and C stands for the speed of light. So the last two things we have left to talk about for nuclear reactions are nuclear fission and fusion. So for fission, it's where you have a very heavy nucleus that splits into smaller ones. And when that happens, it releases energy. And that energy can be in the form of alpha, beta, or gamma rays, and then other energy. So depending on what the amount of energy will depend on the type that is released. And then also more neutrons will come out after that nucleus has been split. And when those neutrons come out, it can cause a chain reaction that then those neutrons can go and split other atoms. This is what we see in nuclear power plants and bombs. Fusion is just the opposite of nuclear fission. So here we are now taking smaller nuclei and combining them to form a larger, more stable one. Fusion releases more energy than fission and is cleaner, meaning that there's little radioactive waste that's actually given off. This takes a ton of heat and pressure. This is what happens in the sun and in hydrogen bonds. This picture shows the difference between fission and fusion. So here we have this neutron that comes and collides with uranium-235. So as it combines, it goes then to uranium-236, because that neutron combined with this one increased the mass by 1. and then that shoots out and divides that nucleus into two smaller atoms, and then more neutrons are released, and then these neutrons can go and trigger more reactions. So this barium 144 and krypton 89 are more stable than the uranium 236. Here over here we have fusion. So two smaller nuclei, they combine to form a larger one. In that process, a neutron can be released and we have a larger, more stable nuclei.